All right, hi everyone. This is going to be a lesson for pre-calculus for inverse trig and right triangles. Now, if you've been watching all the video lessons up until this point, you know that we've already talked about inverse trig. Back when we had our whole chapter about the unit circle and we learned about trig functions, we had a lesson about inverse trig back then. And that was good. That was inverse trig in regard to the unit circle. And now we're going to revisit inverse trig from the perspective of triangles. So let's go ahead and get started. All right, inverse trig and right triangles. I've decided to start this lesson with a little warm-up problem. I thought it would be good for you to get some more practice on evaluating trig functions. So we did this last time in the previous lesson, but I'd like you to do these three. So I'd like you to pause the video and try these three problems. Okay, so these are just warm-up problems. We're not technically doing inverse trig on any of these. These are just evaluate trig functions. So let's talk about them. We've been able to evaluate trig functions at all kinds of values up until now. Typically we've been doing them in radians, probably more often in radians instead of degrees. So that's why I wanted to make sure we got some of these in. Because all the ones we did back when we were talking about them as t values, now we understand that those were really radians. Typically we would draw a scratchwork unit circle, right? And you could do that if you want, but I think what I'm going to draw is just a scratchwork picture of the angle. I don't have to draw a circle. I can just draw an angle. So 135 degrees, what does that look like? Well, if we start in our standard position, I know what 90 degrees would look like. 90 degrees would be if the angle was pointing straight up. And 180 degrees would be if the angle was going all the way to the left. Remember, from starting position. So 135 is exactly between 90 and 180, right? So it's going to be pointing in this direction. This is what 135 degrees looks like if it's in standard position. And we want to know what cosine of this is. Well, we could use a reference angle. Remember that idea? Let's get another color pen. What would the reference angle be? Well, the reference angle is supposed to be kind of the smallest angle that connects this ray with the x-axis. So it would be this right here, which my blue pen doesn't seem to be working. All right, we'll do this with the black pen. This is the reference angle of 45 degrees. Let me zoom in on that. The main angle that I'm interested in is 135, and I'm saying we can use a reference angle of 45. Why did I choose 45? Because that's the angle that it would take to get me to the x-axis. How do I know? Because these add up to 180. So we could talk about cosine of 45 degrees. That's take cosine of your reference angle and see what you get. Well, cosine of 45 degrees is easier. I know that one is the square root of 2 over 2. If you don't remember that, maybe try converting it into radians, and maybe then it'll be easier to see that this is square root of 2 over 2. That's good for the reference angle, but 135 degrees is in quadrant 2, where cosine is negative. We talked about this last time. So the actual answer that we're looking for, it's going to be some form of the square root of 2 over 2. We were just trying to figure out, is it plus or minus? And it's going to be negative square root of 2 over 2. That also makes sense if I think about it in terms of what we know from the unit circle. For part B, a quick sketch of what does 210 degrees look like? Well, I was saying that 180 would, from our standard position, 180 would be pointing to the left. So I want to go 180 plus another 30. So 210 might look something like this. Let's zoom in on that. So if I want to use this idea of a reference angle, what do you think we'll use? The reference angle should be the small angle that sort of connects this ray with the x-axis. So this right here. What is this little angle right here? That would be 30 degrees. So it's a positive number. It's basically, it's like we're trying to get an angle in quadrant 1. 30 degrees in standard position would point into quadrant 1. Anyway, tangent of 30 degrees. We'll figure out tangent of 30 degrees, and then the answer for 210 is going to be some form of this answer. We'll just have to figure out if it needs a plus or a minus sign. So tangent of 30 degrees, I'm going to skip some of the steps. You know, you could think of this as sine of 30 degrees over cosine of 30 degrees. Simplify, and you should get the square root of 3 over 3. Now, 210 degrees is in quadrant 3. How do I know that? I could just tell it's pointing in quadrant 3. I mean, remember, quadrant 1, 2, 3, 4. So this is definitely in 3. So where tan is, what do you think? Positive or negative? We have a 50-50 chance here. We could flip a coin. I'm going to say it's positive. And that tangent of 210 degrees, therefore, is square root of 3 over 3. Positive. How did I know that it's positive? I didn't actually flip a coin. I know it's positive because all points in quadrant 3 have a negative x-coordinate and negative y-coordinate, right? Any point in this is going to be negative something, comma, negative something. And tangent we could think of as y over x. So a negative over a negative is a positive. It means that you could remember that tangent is always positive in quadrant 3. Finally, sine of 300 degrees. That's a bigger angle. Let's draw a quick picture of it. What does 300 degrees look like? Starting from standard position, we go around pretty far, right? If you went all the way around, you would be going 360 degrees. We're going 60 degrees less than that, so we only want to go 300 degrees. So let's go around, almost all the way around, except here. Let's make it look like this. That is going to be my 300 degrees. How did I know when to stop? I stopped so that it would look like there's 60 more degrees left. I stopped so it looks like there's 60 more degrees left to get all the way around. And it turns out that that 60 degrees is my reference angle. So we want sine of 300 degrees, but we could start by finding sine of 60 degrees, and whatever we get for this, we'll figure out if we need plus or minus. Sine of 60 degrees you should be able to do by now. You can do this with unit circle, radians. You could just remember whatever method you want. You should know that sine of 60 degrees is root 3 over 2. Now, what about 300 degrees? 300 degrees is in quadrant. What quadrant are we in? Definitely 4, because they go 1, 2, 3, 4. This is definitely pointing into quadrant 4. And then we have to figure out, is sine of something positive or negative in quadrant 4? Well, it's negative. Because sine, we always learned that sine was the y-coordinate on the unit circle. Y-coordinates are negative down here. So the answer then, sine of 300 degrees, is negative square root of 3 over 2. All right, so that was just 3 little warm-up problems. to kind of bridge the gap between the previous lesson and the one that we're about to do. So this lesson is supposed to be about inverse trig. We haven't talked about inverse trig yet today, but I'm glad we did the little practice problems. Here's what I'll say. Next, what are we going to do in this section? I'm going to say we can combine what we've learned previously about inverse trig. Inverse trig, I'm talking about inverse sine, inverse cosine, inverse tangent, right? We know about those. Combine it with what we've said in recent lessons. And that would mean angles, triangles. I'll just say etc. So let's get a fresh sheet of paper. And in this section, I'm not going to go through the entire definitions of what is inverse sine, what is inverse cosine, what is inverse tangent, because we know those already. But we're going to apply them to triangle problems and see what happens. All right, I'm going to clear all of this away and get a fresh sheet of paper. All right, let's do this. So let's just start with an example so I can show you how inverse trig is related to right triangles. How about a problem that says find the angle theta in degrees and radians. And we're going to be given a picture of a triangle. And we have to be given some information. So first of all, it's a right triangle. Here's the angle theta. We need to be given more than that, though. We're going to be given some side lengths. This one is 4, and this one is the square root of 12. Square root of 12. That could be written differently, couldn't it? You know that I'm a big fan of doing little side notes off to the side. So let's just say note. What is the square root of 12? Couldn't that have been written a different way? Because that's 4 times 3. And we know the square root of 4 is 2. So couldn't we have called this 2 times the square root of 3? I don't know why, but my problem I wrote has square root of 12. I feel like it could have been 2 square root of 3. Maybe we'll keep that in mind as we work on this, just in case a square root of 12 shows up. Maybe this will help us simplify the answer or something like that. All right, but that's all we're given. So what makes this different from the previous section or the previous lesson is that typically we'd be asked something like find cosine of theta or find sine of theta, things like that. But this is telling us to actually find theta. We didn't do that in the previous lesson. We're doing it now, though. Can we find what theta is? I could maybe estimate it by looking at the picture. And say, looks like it's a little less than 45 degrees. But we could find it exactly. So here's what we're going to do. Look at where theta is. That's the angle of interest. And look at which side lengths are given. 4 is what we would call the hypotenuse. Square root of 12 is what we would call the adjacent side. And this other one that's not given is what we would call the opposite side. So maybe I'll list all of these. I'll say adjacent is square root of 12. Hypotenuse is 4. Opposite we don't know. We could find the opposite side length. right? We could use the Pythagorean theorem. If we know two of the side lengths, we could find the third one if we want to, if we think it'll help us. By the way, the adjacent side length, I'm just going to write, is also 2 square root of 3, just in case we want to use that version of it. So how can we find theta? You know, in the previous lesson, when we were asked to find things like, we'd be given a picture like this, and it might say something like find sine of theta, find cosine of theta, things like that. You know what? You know what I notice here? Because we have the adjacent side length, and because we have the hypotenuse, I'm thinking which trig functions between sine, cosine, and tangent. Let's remind ourselves what these would be. Sine of theta is opposite over hypotenuse. Cosine, this is the only time today that I'm going to write this out. But opposite over hypotenuse, this is adjacent over hypotenuse. And tangent of theta is opposite over adjacent. So we should know these from the previous lesson, and I'm not going to write them every time. But which of these three do you think would be the best to work with for this problem? That's something you could kind of do a quick mental check in your head. You don't necessarily have to write all three. I think because we know the adjacent side length and we know the hypotenuse, I think cosine is something that we could work with. I'm going to put a little star next to that for this problem. So for some other problem, if we were given some other side lengths, we might use one of the other trig functions. I'm going to say that we know cosine of theta is 2 square root of 3 over 4. Oh, we could simplify 2 over 4, right? So let's simplify this. Square root of 3 over 2. Now, that's not what the question asked us for. The question asked us to find theta. So we have, so far, that cosine of theta is the square root of 3 over 2. And we want to know what is theta. This is this is a perfect question for inverse trig, in particular, inverse cosine. Let's say theta is inverse cosine of the square root of 3 over 2. We're not finished yet. We're going to try to figure out what this is in degrees and radians. But that makes sense, right? We found cosine of theta is square root of 3 over 2. So theta must be inverse cosine of that number, root 3 over 2. Do we know what this is? Can you remember what this is or figure this out from our previous lesson on inverse trig? I guess in the previous lesson on inverse trig, we probably would draw a scratchwork unit circle. And we would say, do we know an angle that when we take, or you know what? Back then, we probably didn't use the word angle. But we would say, do we know a value of theta that when we take cosine of it, we get root 3 over 2. I do know something that when I take cosine of it, I get the square root of 3 over 2. There's this one here. Root 3 over 2, comma 1/2. Right? I'll zoom in on that. There's this point. You might say, what about this other one? Isn't there another one that goes down here? I don't even need to consider that because, you know, first of all, inverse cosine has domain -1 to 1 and range 0 to pi in radians. So I only need to consider from 0 to pi. So from our usual starting position all the way to pi. I'm only considering the top half of the unit circle for this. For inverse cosine, you only could look at the top half of the unit circle. So we just say, well, all right, well, what theta value does this? What theta value does this? That looks like a familiar common one to me. I'm going to say that that is pi over 6. Notice that that is in the correct range. And all that's left, all that's left is let's find this in degrees. So to convert to degrees, do pi over 6 times 180 over pi. Pi over pi cancels out. 180 over 6 gives me 30 degrees. Okay, before we do another problem, something I want to say about this one before we move on. We answered the question. We found the angle theta in degrees and in radians. How did we do it? I guess we looked at the right triangle. We figured out which side lengths do we have. We have the adjacent and the hypotenuse. And then we thought to ourselves, which of the trig functions is going to help us for this particular problem? And since we knew adjacent and hypotenuse, we said, let's try cosine. We said cosine is going to be this over this, which happened to be, look at that, it happened to work out to be a familiar number. And that's often what's going to happen in these problems, is this works out to be a familiar number. You say, all right, cosine of theta equals that familiar number. And I'm like, oh, I know cosine of pi over 6. Cosine of pi over 6 is going to equal square root of 3 over 2. So that is the answer in radians. And then this problem also wanted us to convert it to degrees. Typically, you would find the answer in radians first and then convert it to degrees if the problem tells you to have both. Some problems might just say one or the other. One thing I want to point out is that, remember, inverse cosine has domain -1 to 1 and range 0 to pi. The range of inverse cosine is 0 to pi radians. It's always in radians. So if you say inverse cosine of something equals, your answer has to be in radians. All right, we don't say degrees. We say, you know, degrees was a separate line, right? But I'm just saying inverse cosine of square root of 3 over 2, it equals pi over 6. It's a function, so it can only have one, answer, and it is pi over 6. All right, let's go and do another problem. I guess my point of that is that that's why we typically find the answer in radians first, because that's what inverse cosine naturally gives us, right? Inverse cosine naturally gives us something that's in radians, and then we do one extra step to find it in degrees. Okay, here's another problem. Instead of giving us a picture, this one is just going to give us some sentences. This says, one of the angles in a right triangle is theta. The adjacent side length is square root of 3. And the opposite side length is 1. Find theta in degrees and radians. Let's see. Why don't you give this one a try? Why don't you try this out? You could pause the video, take a minute or two, and see what you get. All right, so this one didn't give us a picture, but you know, it told us two of the side lengths, so that's just as good as a picture, right? I mean, adjacent, opposite. So I'm thinking through the three trig functions, which, you know, what is sine, what is cosine, what is tangent, and which one is going to help us if we know the adjacent and opposite sides. And out of those three, I think tangent is going to help us, right? Because tangent of this angle theta is going to be opposite over adjacent. Technically, if you wanted, there is another trig function that might help, and that's cotangent. But I don't want to use cotangent because, well, I think tangent is simpler. But basically, we're going to be doing the inverse trig function. We're going to be doing inverse tangent. I would just much rather work with inverse tangent instead of inverse cotangent, personally. All right, so opposite over adjacent. So this is 1 over the square root of 3. Can we figure out what theta is from this? It's a little bit harder when the problem involves tangent, right? I think problems with sine or cosine are a little easier. We could think of the unit circle. Maybe it's a common value. Tangent's a little trickier. But one thing that you could do is you could think of tangent as sine over cosine. That's always true. So maybe that helps. Do we know a value of theta? Value of theta that when I do sine of it over cosine of it, I get 1 over the square root of 3. It's a little tricky. You might have to try a couple of different values. But I think to myself, where does the square root of 3 show up in trig? Like, where does it show up for cosine? How about this? I'm trying to think of a point on the unit circle that when I take sine of it and when I take cosine of it, it's going to simplify to 1 over the square root of 3. It might not equal, sine of theta might not equal 1. Cosine of theta might not equal the square root of 3, but they will simplify to this. And the point that I have in mind is 1/2 over square root of 3 over 2. These are equal to each other. Right? So I'm thinking about the point, square root of 3 over 2, comma, 1/2. That point on the unit circle, I don't know, I'm zooming in a lot today because I feel like I'm writing small. Maybe I'll try to just write bigger. This point on the unit circle has this for sine, this for cosine, which simplifies to 1 over square root of 3. So tangent of theta equals 1 over square root of 3. That point, where is it on a scratch work unit circle? Where is it? It's about here. Right? So let's, over here, let's say that theta is equal to inverse tangent of 1 over the square root of 3. And what do you think theta is? What is this angle that gets us to this point? There is a certain angle, we could think of it in degrees or radians, that gets us to this point, this common point on the unit circle. It happens to be pi over 6 again. It's the same answer we got in the previous problem. That's just a coincidence. In degrees, it's 30 degrees. All right. And this is the same inverse tangent that we talked about in a previous lesson. It has domain all real numbers for inverse tangent. And the range is negative pi over 2 to pi over 2. And this is in the correct range. Okay, so we answered this without even having a picture. I guess if we did have a picture, now we know what the angle theta is. Maybe now that we're done with the answer, it'd be easier to draw a picture now. Yeah, 30 degrees for theta. We know an opposite side length and an adjacent side length. We could figure out the hypotenuse. We could probably solve the triangle. Anyway, let's move on to another one. I want to tell you something. I want to tell you that inverse trig isn't just for right triangles. You know, there are other triangles to consider. From the previous video, or the previous lesson, we had a problem that said, given the following picture, find cosine of theta. All right, let me draw this picture. So we're revisiting a problem that was in the previous lesson. I remember us doing this. This was a triangle that was not a right triangle. There's an angle theta. And the vertices of the triangle were labeled on this one. Remember this? I think it was the only one we had that was this type of problem. So it's not a right triangle because I don't see any right angles in this. I don't see any way that there could be a right angle in this picture. And we found in that lesson, cosine of theta was negative square root of 2 over 2. Okay? Now, you could also be asked, given the above picture, find theta in degrees and radians. Now, I want us to be careful. Let's talk through this together. We're going to do this. We're going to find theta. But let's slow down before we do this. The two problems that we've done so far in this lesson were both right triangles. You know, we thought about sine was opposite over hypotenuse, cosine was adjacent over hypotenuse, tangent was opposite over adjacent. We used all those kinds of tricks. And then we said, all right, well, which trig function would help with this particular problem? We can't do that. We can't do that for this problem because it's not a right triangle. Those three rules, you know, sine equals, cosine equals, tangent equals, those are only for right triangles. There's no such thing as a hypotenuse in this picture. Because there's no, you know, the hypotenuse is supposed to be the thing that's across from the right angle. There is no right angle. So we can't use those kinds of tricks for this kind of triangle. But that's okay because you could go back and look at how we found this in the previous video. And once we find this, then we can finish finding theta. We could just say theta is inverse cosine of negative square root of 2 over 2. I'm not calling any of these three side lengths by, you know, adjacent, hypotenuse, or opposite. Anyway, do we know a value of theta that when you take cosine of it, you get negative root 2 over 2? And I'm just going to think of this in terms of radians, you know? In terms of radians, you know, here's pi over 2 on my little picture. And I'm thinking, what about right here? What about going this far around to this angle? Doesn't this get us to the point? Negative root 2 over 2, comma, root 2 over 2. What angle is that? What angle is that? It's going to be 3 pi over 4. And in degrees, you know how to convert between degrees and radians by now. I don't have to show that every time. It's 135 degrees. And you could either do the steps to convert it to degrees, multiply it by 180 over pi and simplify. Or you might just look at this picture and say, I remember that that's 135 degrees. Because 45 more would take me to 180. Okay. So that was just to show you how the problem we had in the previous lesson where we found cosine of theta, now we could go a step further. And once we have found cosine of theta, we could actually find theta. And it's not a right triangle. All right, something else for me to tell you. Inverse trig and triangles, and I'm going to say usually right triangles, can help us solve some word problems. So I've got a couple of these. Let's see. I'm just going to get a fresh sheet of paper for these. All right. I think I've got two, and I'll do the first one. So, example. A 25-foot tall flagpole. Or, you know what? I said that I have two problems. I think I might actually ask you to do the first one. So, wait till I finish writing all this. Casts a shadow 38 feet long at a certain time of day. I mean, it makes sense that the length of the shadow is going to change throughout the day, right? What is the angle of elevation of the sun? So, what I want to say is that we did a similar problem to this, I think two lessons ago. 2 lessons ago when we were learning about right triangles and angles and trig functions. We found, I think in that one we were trying to find the height of the flagpole. So it was similar, but this one is asking us to find the angle. So I'd like you to take a couple of minutes and try this and draw a picture if you think it'll help you, and then check back with me. All right, so hopefully you tried this. So, a couple of hints. I mean, one hint is that this is similar to that problem from 2 videos ago. Another hint is that the picture is going to be similar. Similar situation. So let's draw a side view. Let's make the ground flat. Let's make a flagpole. You don't actually have to draw the flag. You just need, there's a flagpole, and there's some angle of elevation to the sun. Remember we talked about what that looked like. It meant that the sun is going to be up here. Now, just by drawing this, it seems like I'm making some assumptions about what the angle might be. I mean, how do I know that it's like this? Maybe the sun is up here making a different angle, or maybe the sun is over here relative to the flagpole, making a different angle. For the picture, it's not really that important. We just want to make an angle so that we can label it theta. And if it turns out that maybe our picture is not drawn at the correct scale, that's okay. That's okay. If it turns out that, this to me looks like maybe around 30 degrees. And if the answer turns out to be, 70 degrees, that's okay. The picture is just a tool to help us. Here's the shadow, which we know is 38 feet. And the height of the flagpole, we know that is 25 feet. So, yeah, it's different from that other problem because I guess in that one we knew theta and we wanted to find the height of the flagpole. How about this? Let's think about the 3 side lengths of this right triangle. I'm going to draw the little box here because this is a right triangle. We assume the ground is flat and the flagpole goes straight up. So we could talk about the opposite side length. We could talk about the hypotenuse. We could talk about the adjacent side length. You could write these in any order you want. And I think the opposite side length is given. It's 25. The hypotenuse is question mark. We don't know that. We were not given that. The adjacent side length is the shadow. That's 38. Now, from this, we could find the hypotenuse. 25 and 38, use the Pythagorean theorem. 25 squared plus 38 squared equals hypotenuse squared. But I don't want to do that. I don't want to, unless we have to. I'd rather not do 38 squared plus 25 squared and try to take a square root. I think it's going to be a messy number. I don't think we have to do that anyway. If we were given the opposite and the adjacent, that makes me think that for this problem, we should use tangent. Tangent of theta. Or maybe inverse tangent, right? We're using tangent and inverse tangent. You could think of it that way. Tangent of theta is opposite over adjacent, so it's 25 over 38. So this problem says to find the angle of elevation of the sun, which I've labeled as theta, and it's going to be inverse tangent of 25 over 38. So in this problem, I'm looking at this and I'm thinking to myself, do I know an angle that when I take tangent of it, I get 25/38? Is it one of our common angles that we know? No, I don't think so. It's not going to be any of the common radians we know, like pi over 6, pi over 4, pi over 3. It's not going to be any of the common degrees that we know, like 30, 45, 60. It's not, right? It's 25 over 38 is a weird number. So what I'm going to say is, if this was a problem that was like on an exam where you're not allowed to use a calculator, you would have to just stop here. You'd have to stop here and be like, that's as far as we can go by hand. And that is the value of theta. It might not be as simplified as you would like. I mean, we wish that we could get this as just a number. But right now, at this point in the course, there's not really any way for us to do that by hand. So if it's something where you can't use a calculator, just stop here. You're done. You did find the answer. It's just not as nice of an answer as some of those other problems. But that's okay. I mean, not every problem in this class is going to work out to be 30 degrees, right? There are going to be problems that work out to be weird things like this. Now, I'm going to tell you, with a calculator, I found this to be approximately equal to 33.3 degrees, or 0.58 radians. But that's just kind of something I put off to the side. I needed a calculator to do that. And, you know, I guess now, with that in mind, I would say the picture is probably not too far off. 33 degrees, yeah, that's probably around there. So that was one that I asked you to try. I'm going to do the next one for us. But that just shows you how inverse trig could help us to answer some word problems. Let's do a different one. Let's do one that doesn't involve a flagpole. So this is going to say a 20-foot ladder is leaning against a building. If the bottom of the ladder is 6 feet from the base of the building, two questions. Part A, what is the angle of elevation of the ladder? And part B, how high does the ladder reach on the building? I'm going to do this problem for us. I'm planning to talk us through this, so you don't have to pause and try this on your own. I mean, you can if you'd like to. You know, it's always an option. But I'm planning to talk us through this one. I'm going to say off to the side, kind of as a part of this problem, I guess, I'm going to say assume the building is taller than 20 feet. You know, in math, we like to be precise, and I think when I envision a ladder leaning against a building, I'm picturing the ladder is going to be leaning against the side of the building, and you know, we want to assume that this building is tall. So, is this similar to the flagpole problem, or is this different? I mean, I guess it's asking us, part A is similar, right? Because part A is asking us for an angle of elevation. So maybe it is kind of like the previous problem. Anyway, that's how it's given to us. I'm going to draw a picture. Picture's not given, but I think I can draw one based on the info that is given. Again, I think, you know, let's do a side view of this whole scenario. You might get some other problem later where you think like an overhead view might help or something, but this is a ladder leaning against a building. I'm going to do a side view. So here's the ground. The ground we always assume is flat unless it's specified otherwise. I've got a building. That's a good building. Let's write building on it. And we have a ladder leaning against it, right? So, well, I don't know how much it's leaning. Like, I don't know if it's mostly upright or if it's kind of like almost on the ground. Let's just draw something like, let's draw something like this. This is my ladder. You see how that's a ladder leaning against the building? We'll zoom in for the picture drawing. Okay, let's label some other things that we know. The 20 feet is given in the problem. 20 feet is the length of the ladder. So let's say that that's this length. Hey, you know what? I think we have a right triangle, don't we? If we assume that the ground is flat and the building goes straight up, then this angle here is 90 degrees. So let's label that. Here we go. That's a right angle. Cool. What else do we know? 6 feet. The ladder, the bottom of the ladder is 6 feet from the base of the building. So that would be this here. This length is 6. So that the bottom of the ladder is 6 feet away from the building. I don't know if my picture is exactly to scale. My 6 and my 20, it doesn't, maybe it's not exactly to scale, but That's okay. Part A is asking what's the angle of elevation of the ladder. So which angle is it asking us for? I mean, this triangle has 3 angles in it. It's not asking us for the right angle. The angle of elevation, just like the flagpole problems, is going to be this, theta. So part A is asking us to find that angle. And that's a good picture. We can work with this. In fact, I would even say that now that we've drawn this, you could like erase the building part of it, you could erase most of the ground, and you could just like have a right triangle. And now it's just a right triangle problem. Anyway, what do we know? Opposite, hypotenuse, adjacent. Which of these do we know? I think opposite is not given to us. I don't know how high up on the building that the top of the ladder touches. I know it's less than 20, but I don't know how high up it is. I could find it with the Pythagorean theorem, but let's just list the things that we know for sure. We know this is 20, and we know this is 6. So if we know the hypotenuse, and we know the adjacent side, which of the three major trig functions is going to work with these? I think cosine is the way to go. Cosine is going to equal adjacent over hypotenuse. So we could say cosine of theta is 6 over 20. 6 over 20 can be simplified to 3 over 10. You should do that. Do that kind of simplifying. So theta is inverse cosine of 3/10. Do we know what this is by hand? I'm going to say no. I don't know an angle. Like, I don't know one of our common angles that when I take cosine of it, I get 3/10. You know, our common angles, when I take cosine of them, I get things like 1/2, square root of 2 over 2, square root of 3 over 2, 1. We've never gotten 3/10 as a result. So let's just put a box around this and say that is the answer. If this were a calculator problem, I would say I did find this using a calculator, and it works out to be about 72.5 degrees, or 1.27 radians. Okay. What about part B? I think we can do part B just on the little bit of page that I have left. So all of that was part A. I guess part B is using the same picture, though. Picture goes for both. You know how I said that if we wanted, we could erase most of this picture and just focus in on the right triangle part of it? I'm going to do that here. 6, 20, right angle. And what do you want to call this side here? This is what we're looking for. How high does the ladder reach on the building? It's this missing side length of this right triangle. We could call it H for the height, if you'd like to call it H. I'm going to call it B. You know why I'm calling it B? Because the Pythagorean theorem says A, B, and C. So I'm just going to call it B. And then Pythagorean theorem gets us the answer. Pythagorean theorem says 6 squared plus B squared equals 20 squared. And let's see if we can solve for B. And in the end, at the final answer, I'm going to write feet, because this is supposed to be measured in feet. All right, B squared is 400 minus 36. So I did 20 squared and 6 squared. So B is, well, first of all, when I subtract these, 400 minus 36 is 364, okay? So you think I need to write plus or minus the square root symbol, 364. Except that's not what I'm going to write. I'm just going to write square root symbol, 364. I'm not writing the plus or minus sign. Do you know why? Because this is a height on a building and it can't be negative. This is a length of a side length of a triangle, and it's, you know, it's a real world height on a building. It's not going to be negative. Negative would be what? Negative would be like underground or something. This is we can tell from both of these pictures, we can tell that B has to be positive. So you don't write plus or minus. Okay. Can we simplify this at all? Do I know any numbers that are the square root of 364, like something times itself is 364? No, I don't think so. I don't think so, but we might be able to simplify it anyway. I could tell that 364 is divisible by 2. In fact, I can tell that it's divisible by 4. You know, like I did earlier with the square root of 12? And I rewrote it as 2 times the square root of 3. That's what I'm trying to do here. This is 4 times something. What is it? 4 times 91. So I think it would be nice for us to write this as 2 square root of 91. And I'm going to say that the answer is this many feet. And that's a good answer. That's a good answer. I would like to see this kind of simplifying. I think that this is a little bit nicer. And I did find this with a calculator. In case you're curious, I found that this is approximately 19 feet. So I think that means my picture was not really drawn to scale, because in my picture, this looks like it's less. In my picture, this looks like it's 15 or something like that. And that's okay. The picture was good enough to help us solve the problem. Okay, I've got one more. I'm going to clear away this entire page so you can pause if you still needed to write any of that. All right, let's do one more. And I'm going to ask you to try this one. It's a word problem. This one is going to give us a picture. So wait until I write all of this and draw the picture. A lighthouse is located on an island 2 miles off a straight shoreline. An observer stands on the shoreline four miles from the lighthouse. Find the angle theta in degrees and radians in the picture, in the given picture. So wait till I draw this before you try it. A lighthouse is, can we picture this in our heads? I'm gonna draw the picture before I give you a chance to work on this problem. But what do you think the picture is gonna look like? That's kind of interesting. Lighthouse is 2 miles from a straight shoreline. Observers 4 miles away. I could think of what a picture of a lighthouse looks like. But then in one direction we have to go 2 miles, and in one direction we have to go 4 miles. So I think that the best picture that we could make is an overhead picture. It's not a side view, right? because we need to go 2 miles in one direction and 4 miles in another. So this is going to give us a picture of overhead. This is the straight shoreline. And somewhere off of the coast is a lighthouse shining a light. We're going to write lighthouse next to it. And we know, I'm just going to label the given information, okay? We know that the lighthouse is on an island 2 miles from the straight shore. So this distance right here is given to us as 2 miles. We know that there is an observer on the shoreline 4 miles from the lighthouse. So that's why I left lots of room up here. Somewhere up here is an observer. And the distance from them to the lighthouse is given as 4 miles. And this angle is going to be labeled theta because the problem said there was going to be an angle theta. One more thing. The shoreline is said to be straight. The lighthouse is 2 miles from the straight shoreline. That means this forms a right angle. Okay? So now that you have all of that, I'd like you to pause the video and give this a try. Okay, it looks like we've got a right triangle problem. Theta is maybe not in the orientation we're used to. Like a lot of right triangle problems that we do have the angle of interest theta is usually in like the lower left. This time it's in like the upper right. That's okay. It's still a right triangle. It has a hypotenuse. Here, let's write the opposite side length, the hypotenuse, the adjacent side, if we know them. Let's just try to organize all this information on this right triangle. So the opposite side length is always the side that is opposite from theta. Theta is the angle that we're interested in. And the side length that is on the opposite side is 2 miles. The hypotenuse is always the one that's opposite from the 90-degree angle. So in this case, it's the one that's 4 miles. The adjacent side length would be this other side length of the triangle. I guess the distance from the observer to this point. We don't know what that is. We have opposite. We have hypotenuse. So I'm thinking of the 3 major trig functions, sine, cosine, and tangent. I'm thinking which one works best with opposite and hypotenuse. And I think we should use sine. So some of the problems that we did today used cosine. Some of them used tangent. This one's going to use sine because sine of theta is opposite over hypotenuse, which is going to be 2 over 4. Hey, 2 over 4, that's also known as 1 over 2. Sine of theta is 1/2, so theta is inverse sine of 1/2. By the way, when we're working on problems like this, when I ask you to pause the video and try it, you know, if you may have gotten all the way through it, or you might have just gotten halfway through it or something, when I'm going through the solution and reviewing it, it's always a good chance for you to, you know, pause and fix things that you might have messed up and see if you can finish it from there. Whatever works for you. Do I know an angle that when I take sine of it, I get 1/2? All right, so I know 2 angles that when I take sine of them, I get 1/2. There on the unit circle, there's one that's here, and there's also one that's here. Okay. Let me ask you something. Is it even fair that I'm automatically saying theta is inverse sine of 1/2? You know how inverse sine of 1/2 only has one value? Pretend I didn't write this. Pretend I just wrote sine of theta equals 1/2, and I'm trying to figure out what theta is. Do we automatically have to use inverse sine? You might look at this picture of the unit circle, and you might say, I can think of two different angles. I could think of this angle, which I'm just going to write it in degrees. This is 30 degrees. But I can also think of this angle. Doesn't this also have a sine equal to 1/2? And this is 150 degrees. Now, if we do inverse sine, we only get one answer. We get the smaller answer, right? Because there's a certain range and domain for sine and inverse sine, you know. But looking at the picture, I'm like, well, I can think of two different angles that when I take sine of them, I get 1/2. Which one is the answer to this word problem? We could also convert these to radians, by the way. 30 degrees is pi over 6 radians. All right, I am going to say that pi does equal pi over 6 radians. And theta does equal pi over 6 radians, and that does equal 30 degrees. But why did I just completely throw out the other answer, the 150 degrees? We answered the problem, but I'm just talking about it some more. So I'm going to say, even though sine of 5 pi over 6, also known as 150 degrees, equals 1/2, we can tell from the picture that the answer can't be 150 degrees. That's why. That's why I didn't say 150 degrees, because look at the picture. How big is the angle theta? I've told you that when there are pictures that are given, or when we draw a picture ourselves, it might not be drawn exactly to scale. Okay? But it's going to be drawn close enough, and I can tell that there's no way that this little angle here is 150 degrees. So, given the choice between the answer is 30 degrees or 150 degrees, 30 degrees is the only one that makes sense. Also, even without the picture, a right triangle can't have an angle of 150 degrees. Can you see why a right triangle can never have a 150-degree angle? I'll write it. Because one of the angles is already 90 degrees. And all three angles must add up to 180 degrees. So those are two ways that you could tell that, technically you might say it looks like there were two potential answers, but we can rule one of them out and we can say 30 degrees has to be the correct answer. And that is why it's okay to just use inverse sine, because inverse sine gets us the correct answer. in a right triangle problem. Okay? All right, so we're going to wrap up in a second here. Okay, so that was our section on inverse trig and right triangles. It was mostly right triangles, but I think we had one problem that was not a right triangle. So a couple of different types of problems in there. Some of the problems just said, like, here's a picture, find theta. That's one type of problem. And then there were word problems. And, you know, we saw a word problem involving a flagpole, a word problem involving a ladder, and a word problem involving a lighthouse. And I think, if I'm not mistaken, that we've seen that those three problems, we wound up seeing today problems that used sine, problems that used cosine, problems that used tangent. I purposely made sure that all three showed up today. So you have to use whichever one seems appropriate for the problem. Depends on what information is given. I know that sometimes tangent is a little bit tougher, but sometimes it's the best option. Let's see, what else can I say? Because this is pre-calculus, I want to address one thing because this is pre-calculus. These types of problems that we're doing, I think, are pretty important because, you know, presumably most of you are planning to take Calculus 1. And I just want to tell you, we like to say like little previews of Calc 1 here and there. The ladder problem. I've seen variations on that in calculus where, you know how we had a ladder leaning against a building, ladder was leaning against a building at a certain angle, whatever. In calculus, you might see a problem like that where it says a ladder is leaning against a building and it's slipping, it's sliding down the building, it's moving. And then you'll be given some information about how fast it's slipping and how fast it's falling. And then there'll be some question like, how fast is the angle changing? Things like that. It's kind of like some of the problems that we're doing right now. You could have calculus versions of the problems where what we're doing is like a snapshot of everything is completely motionless. But the calculus versions of these problems have like a moving element. Like, for example, consider the lighthouse. What if the lighthouse problem was, instead of a lighthouse, what if it was a boat and it was moving? It would change the problem a lot, right? Because if the boat was moving, the angle would be changing, the distances would be changing, and then you'd have to have some other information given and some other kind of question. But yeah, you know, that's one of the ways that this class is trying to prepare you for calculus, is we do these types of problems, and then you see moving versions of these problems, you know, in another semester. Okay, so that's going to be it for now. Pretty interesting. And yeah, thanks for watching. I'll see you next time.